Okay, so welcome everybody here. I just arrived 15 minutes ago, so I probably haven't met any of you, but I'm looking forward to meet at least some of you today and tomorrow. But I'll start with presenting myself and then talking some about Java Virtual Threads and what I learned, or what my team learned when we implemented support for Java Virtual Threads in GlassFish application server. And then I hope you will have questions either now. You can ask questions here in Slido, or whenever you meet me at the conference, let me know, or you can connect to me with via social media, internet. I'll be happy to chat with you about anything. So I hope you already know how to connect to Slido.com and raise a question. You're in room 1, but I think you know it already too. So I'll proceed with my presentation. So first, shortly about who I am. I'm a Java champion, so if you have any questions about Java champions, I can answer them for you. But that only means that I like to go conferences. I also lead the Java user group in Czech Republic, in Prague, where I now live. I'm also quite active in Jakarta EE. I'm a member of some specifications teams, and I'm Java developer. I provide trainings for Java, for Jakarta EE, and I'm very familiar with GlassFish. I've been working internally with it and providing support for it for customers for a long time. So if you have any questions about Jakarta EE or specifically about GlassFish, I'm here, or anywhere on the internet. So now I'm going to talk about virtual threads and why. Because I believe it's a very good thing. And I love Duke, and I think it's very close to how I love Nuke. I love virtual threads because it's a very new thing that already was in some languages a couple of years ago or for some time, but it took some time to get into Java for valid reasons, because the Java team obviously wants to make everything perfect. But we were also lucky that they were releasing parts of it or actual status of it as preview versions in the past releases, so we could have a look. Some things were changing, so if you studied it like 2 years ago, what was the status, and remember some limitations from there, from that time. A lot of improved since then. And in Java 21, there are very few limitations, but I'll talk about them later. So now virtual threads are in a very good shape, and I'm going to show you why you should try to use them, when you use them, and when maybe you should not use them. So maybe some people love Java modules. Probably not. Who loves Java modules? Yeah, they're very make it very complicated to upgrade to the new Java version, right? Have you tried upgrading an application server or something big application from Java 11 to Java 17 to Java 21? You always have some more and more restrictions with Java modules. But I love lambdas, and I think Java virtual threads are the second biggest thing, or like the next big thing after lambdas. Like Java lambdas changed the world of Java in Java 8. I believe virtual threads are going to change the world of Java after Java 21. And why? First, have a look at traditional threads. Why they are cool, why they are not so cool. They are actually quite cool because a lot of languages don't have good support for threads. So a lot of people, programmers who use languages, they don't know how to use threads because their favorite language doesn't support that. Like JavaScript in the browser doesn't know anything about threads. I think now Node.js for a couple of years already has some support for threads, but in the beginning there were no threads. So we were lucky to have support for threads in Java from the very beginning, and we could do very performant applications utilizing all the threads that are available on the system. But still, there's much to be improved. This is how it looks like. when you create a thread in Java. There are also new ways how to do it, but this is the very basic. The problem with this is that at the very end, first you create like an object, this just Java object. But when you start a thread, it actually calls operating system, and it creates a thread in the operating system, which is a system call which is not that fast as just normal Java call, normal computation, or just calling a method on an object. So it can get little slow when you need performance. So in the end, you don't want to create new thread anytime you need a thread. It's better to create a thread and then reuse it for multiple things. Another thing is quite slow with threads. It's context switching. If you have a lot of parallel tasks running, like 1,000 parallel tasks, but you only have like 8 CPU cores, they cannot really run in parallel. Only 8 tasks can run in parallel. And the operating system needs to switch from time to time so that another thread uses the CPU, then another thread. So it tries to be fair to all the threads that want to use the CPU. But it costs some time to switch the context on the CPU. So it has to remember the state, move it out of the CPU, then fill the CPU with new threads, set the registers as they were there before when the thread that's going to run was running before. And it's, again, not so performant. It's better to have less parallel tasks and tasks in queue, and these fewer parallel tasks will not need so many context switches. They will just use the cores. And then when they are done, more tasks on the queue will be assigned on the CPU. This is the way how you can reduce these context switches, but they are always there. And another thing about threads is by design in the operating system, how they work with memory is every time you create a new thread, operating system reserves some amount of memory for that thread, for the stack trace actually. When you call a method and another method to remember which method was called before, which arguments it had, and all the local variables, it needs to store them somewhere. And this is the infamous stack trace, which you see when you get an exception. And this may not take so much memory, but the operating system reserves some memory. So you may not need that memory, but every time you create a thread, it needs to reserve the memory. And then if you create more threads, like with this code, for example, then you're out of luck. Let's see what happens. If I run this code, this is a bit more sophisticated version, but actually here I create a lot of threads so that they still live and do something, or actually they don't do something, but I need to keep them because otherwise they would be gone and I wouldn't have so many parallel threads running. I make them to sleep, just to block them, and I create a lot of threads that just wait. But even though they do nothing, they still reserve memory. They don't consume so much memory, but they do reserve it. And when I try to run it, I'll make it like this. Yes. And I'll tweak the parameters. So when I need to switch to Java 21. I still haven't set Java 21 as the default one. So now it's creating threads, but when it gets to some certain number, you get an error and you're gone. Your process is gone, you cannot do anything about it. If you create too many threads, you're just out of luck. And I don't know, by some virtue, it is this specific number somewhere. This. So when you create this amount of threads, at least on my system, it's always going to kill your process. And it's always the same number. I tried it multiple times, it's always the same thing. So I don't know what is actually why it's that number, but what is actually happening when you create so many threads. For each thread, by default, operating system will reserve 1 megabyte for the stack. And when you create these 32,000 threads, it means that it needs to reserve 32 gigabytes of memory, just for your single process, and just for the threads. It doesn't count heap. So if you already have something on heap and you need some memory to account for that, it's more than 32 gigabytes. This is just to reserve it for threads. And in reality, this small thing is what the thread really needs. This is the memory utilization. So if we look into detail to our process, we would see that the real memory, the residual memory is small, but the virtual memory is very big because it needs to reserve all this and it's not going to use it, most probably. So that's one of the problems with platform threads. That's why we have an answer in many libraries, in many frameworks, also in GlassFish, many application servers do that. We pool threads. So we create a thread and we use it to run one task, but when it's done, we don't kill it. We restart it with another task. So we give it a queue of tasks, and every time there is something on the queue, it will pick it up and do something and then wait for a new task. And we also limit the amount of threads because of one of the reasons is this, that we don't need to reserve so much memory. So we can limit it to 1,000. Then we can process 1,000 parallel tasks, no more. The rest is on queue. But we have quite good throughput with 1,000 threads, for example, and we don't need that much memory reserved. This is how thread pools work if you still haven't studied how it works. Thread pool, basically in Java, if you saw the executor service or executors, is the same thing. It's just a different name. Executor is basically thread pool, or an abstraction, because you can have an executor that doesn't create thread pools, but usually they do. They create several threads, and when a task is in the queue, the thread will execute it, and then we'll come again to the task, to the queue. If there is no task, it will wait. It will not finish. Again, it will ask after some time, or when there is a new task in the queue, one of the threads that is idle is resurrected, and it executes the task. If there are too many threads that are not doing anything and you probably don't need them, then the thread pool usually removes some of them, but not all of them. It still wants to keep some of them ready in case of tasks come to the queue. There are also problems with this, because you may use thread locals in your threads, and then what happens with thread locals? Thread locals are removed from memory under two conditions. When you call a remove method, remember thread local is basically a container for a value. So set it to a value, you modify the value, but you can also remove the value from that container. If you don't do that, it will stay there until the thread is discarded. So remember here, we keep the threads. So it will always stay there until the thread is really dropped when it's idle for a long time. So that's one problem. You can introduce memory leaks pretty easily if you use too many thread locals and you forget to remove them after you're done with them. Then it may happen even if you have 1,000 threads, maybe they are stuck on some slow database query, a lot of them. Maybe somebody issues like 1,000 requests on your application, and all the requests are going to database, and they need to wait for it. What worse can happen is they become stuck in a deadlock. They're waiting for some semaphores and for some synchronization primitive held by one thread, and all of the new threads are waiting for this, so you can easily starve all your threads in the thread pool. If your application is not designed well, or under certain conditions when too many people try to do the same thing and you need to synchronize, and ideally it will recover later, but if you have a real problem in your application, real concurrency issue, it may become the application may become deadlocked, and it's not going to resurrect itself. It will just stay there. And then thread pools are basically an abstraction of a thread, so you need to work with them. You need to set up how many threads you want to in the pool. Sometimes you don't guess that right. Maybe you need more of them to increase performance of your application. Maybe you need fewer of them because you need more to save more memory. Sometimes even fewer threads are more performant than more threads. If you execute, as I said before, if you execute only 10 tasks and you have 10 cores on the CPU, it may be more efficient to do 10 tasks, then 10 tasks, then 10 tasks, rather than run all of them at once on 1,000 threads, because then they would have to switch context on the CPU. So, yeah, what can we do better? Until Java 21, we couldn't do much more than introducing reactive programming, but I'll talk about that later. In short, reactive programming may be more performant, but it's very hard to write the code, debug it, understand the code. So there's lots of complexity behind just getting 10 or 20% performance, or maybe avoiding some deadlocks or some situations. So you can end up with a better application that performs better, but the maintenance cost is much, much bigger. So welcome virtual threads in Java 21. What is the promise from virtual threads? They are fast to create. So if you want to create and run a thread, it's almost in no time, because you don't need to call the system. The virtual thread is just a concept within the virtual machine. Virtual machine controls them. And then it needs some operating system threads to execute them, but it doesn't need so many real platform threads to run a lot of virtual threads. So creating a virtual thread is fast. Also context switching is fast, because it also happens in the Java virtual machine. You don't need the virtual machine or operating system don't have to do anything with any system call to switch between two virtual threads. It's just like Java virtual machine tells one thread to stop and shifts some object and tells another virtual thread to run on an underlying operating system thread. So it's sort of like Java virtual machine creates a thread pool of platform threads, and then it schedules virtual threads as tasks on these threads. I think I have it's much later. Yeah, this is a graphic that I want to show later, but here it is. You have many virtual threads, then you have just a few carrier threads. They are called carrier in Java terminology. They carry this virtual thread to do the work, but then when virtual thread doesn't do anything, it's blocking or it's done, it's detached from its carrier thread, and some other virtual thread runs on it. So it's very similar to thread pools, really. It's just that you don't have to handle them yourself. These are handled by the Java virtual machine. And the result of this, because they are so lightweight, you can run a lot of them. You can start them very fast, so you can start millions of threads very fast. You can switch between them very fast, so it's not an issue to create 1 million, 2 million, 10 million threads. The only thing you need is heap, because the stack is now stored on heap. Remember, in platform threads, the operating system threads store it in a separate memory, which is pre-allocated, usually 1 megabyte. In virtual threads, it's just virtual object, everything is on a heap. But that also requires memory. It's just the difference is that it requires only memory when you really need that memory. It doesn't need to pre-allocate anything. So when there is something to store on stack trace, or some stack trace to store, then it stores it in memory. But yes, in reality, you need to increase the heap size if you create a lot of virtual threads. Not only because it stores stack trace, but because it runs your code, and your code probably creates some more objects. So it's more memory heavy, but it can improve performance, simplify your application. I did some measurements running a simple application that listens on a network connection takes the connection and then runs some simple task on a thread. And in one case, it ran it on a thread pool, like the standard thread pool from Java, which is probably not super sophisticated, but good enough. And it uses platform threads. But in the way that I described earlier, it limits the number of threads and it reuses the threads. So it's pretty performant. And then I also did the same thing with virtual threads, where I create a new thread every time. For every time there is something on the connection, I want to run a task, I create a new virtual thread. And even if I create new virtual threads, I ran a benchmark according to this, against this my application, which runs 10,000 requests all the time in parallel and storms my application. And I saw, just by switching to virtual threads, I saw about 15% performance. It's not like sophisticated like science measurement. I did it on my computer. I did it several times and compared. So in reality, it may not be that big difference. It may be a bigger difference, but I saw that there was a performance increase. On the other hand, when I compared memory consumption, the real memory consumption was bigger with virtual threads. Only the platform thread version was had to reserve the memory, but it didn't use it really. So the real memory usage was bigger with virtual threads, but the performance was better. And just to show you something, the same thing, but just with virtual threads, I'm going to create as many virtual threads as I can. And the only thing is, I change how I create them. So here I had the condition to create platform threads by default. But if I have the virtual threads, the -v option, and I'll rather increase memory size, or maybe 4 is enough, just to show you what happens. So this number on the left is millions. So it's now saying 9 million threads created. And it's growing and growing, and then it stops to grow. Do you know what's happening? When you almost always, when you have an application, a Java application that is stuck and doesn't do anything, it's almost always garbage collection, yes. So that's because just these threads, they don't do anything, they just sleep, but they still require some memory, and they fill the whole heap. I have 4 gigabytes of heap, they filled it with 9 million threads, fill the whole memory. Now garbage collector is trashing my CPU. I don't have time to show you everything, but CPU is really high now, and after a while it will kill the process because it cannot allocate more memory. But this happens after 9 million. And if I create, now I can't even kill the, I would have to, that's why I have this PID here, so that I can kill -9. And then I kill the process. But the process is not responding, it doesn't even respond to my kill signal. So this happens. So then you increase more memory, you increase memory to 10 gigabytes, and you can create more. I think around like 20 or 30 millions or something. This is 20 millions already, and now, boom. So we got a little further. I'll keep it running so that you see that it really runs out of memory and stops. And I'll go back to the rest of my presentation. So how virtual threads work? I already said that there are basically plain Java objects. The real work is done still by the underlying operating system thread, but the trick is that the virtual machine creates a pool of these operating system threads, usually 1 per CPU core, so to avoid switching context. And this context is switched on the virtual machine level. So it's basically just when one thread is done with something or is going to block something with an IO call, then it says Java Virtual Machine to move it away from the underlying platform threads. And then virtual machine runs instructs another virtual thread to run on this specific thread that is now free. But the thing with this is that this happens when the thread asks the virtual machine. So that's what took a while to the designers or to the architects of Java to redesign all the I/O calls so that the virtual thread can instruct virtual machine that is going to do an I/O call, and the virtual machine then can put it off and schedule something else that is going to do real work while the other thread is waiting. And you can also call thread yield. Then it also instructs the virtual machine to check if it wants to schedule some other thread instead of the current thread. But if you don't do anything like that, if you just do heavy computation, like a lot of Fibonacci numbers, a lot of like prime numbers without any I/O, then virtual machine will keep it running on the same thread and will not interrupt it. So that's little downside. So if I wouldn't use virtual threads on computing heavy applications, because then what really happens is that just only few threads are running on these few underlying system threads, and when they are done, only then another thread can run on them. So we would be limited only to like 10 or 20 parallel computations, and everything else would have to wait. They are more convenient on most of the applications, I would say, that use I/O operations, that go to database, connect to something on network, read something from file system. Even if you sleep, called thread sleep, it's a blocking operation. So all these instruct the JVM to replace the thread and make some other virtual thread that actually can do something, use the underlying thread. So this is the picture I already showed. And it only demonstrates, like, you can have millions of virtual threads, only a few carrier threads, but there is a mechanism in Java Virtual Machine that replaces the virtual threads that are running on one specific carrier thread, but it has this limitation. The virtual machine has to be instructed to do that. Unlike operating system, which can actually send an interrupt to processor, and then this interrupt will cause switching the context. At any point the thread is doing anything, it will just pause it, move it away from processor, and schedule some other thread. This doesn't happen in Java Virtual Machine. In Java Virtual Machine, it only happens when a thread calls with virtual threads, only if virtual thread calls some blocking operation. So now I'm getting to my real experience. It's still not very long experience, like just a couple of weeks and months playing with it while I implemented support in GlassFish. But I did some measurements also on GlassFish. And just to introduce what can be done in GlassFish is basically two ways. Is to automatically execute incoming requests, or when there is a message-driven beat on WebSocket, anything that comes to your application, automatically schedule these tasks on a virtual thread. That can be done in the server itself. You can just configure the server to do this on virtual thread. You don't need to do anything in your application. And then another thing is that is coming in Jakarta E11 and the new version of GlassFish is an executor. Executor is already there in GlassFish in Jakarta E, but it's used when you want to schedule a background task and you want to run it on a different thread. Then it creates a thread that has all the information that it needs from the server. You don't need to start anything, configure anything. It will just be capable to inject things. It has notion of JNTI tree, so you can write full Jakarta E code in this new thread, but you create it with executor, you submit some task, and it runs on a thread that is created by the server. But this always been a traditional thread, and there was always a thread pool behind it. Now with Jakarta E11, there's one simple change in the API. This is this virtual thing here. That is just a hint for application server. So if application wants to create an executor with this virtual true, and server is capable of creating virtual threads, then it will create virtual threads instead of platform threads. And then it doesn't have to do a thread pool. It can create a new thread every time a task is submitting. So in the end, when you call the last line, executor submit with something, that something will run in a virtual thread. Automatically, you just need to give a hint to application server that it should create a virtual thread executor and not a normal executor with platform threads. So I'll come a little bit back. So what we did in GlassFish is that we created a special executor service that replaces the default executor service in GlassFish, or concretely in Grizzly HTTP stack. And with this, all incoming HTTP requests are executed on a servlet or a REST resource with virtual threads. So you don't need to change anything in your application. You just need to add this. Currently, it's a separate jar file, so that you need to add it to GlassFish, and then you configure GlassFish to use this class of this executor service instead of the default one, and you get it out automatically for any application. As a result, there should be a better throughput, although when I did measurements, we still didn't get better throughput. It was more or less like the same as platform threads with a thread pool. I expect that the thread pool in Grizzly is so optimized that it's really hard to get better performance with virtual threads, but that's just my hypothesis. I saw a better performance with GlassFish, with a simple application, than with that application that I told you about in the beginning, which is very simple and gets just HTTP request from a connection and schedule it on a thread, either platform or virtual. With full GlassFish, you get better performance, which is quite impressive because GlassFish has a lot more inside. It supports a servlet, and it runs the application as a servlet in a servlet container. So it does this translation from HTTP request to a full servlet request and then back to HTTP response. But for some reason, I wasn't able to code a simple application that just does something like that in the most straightforward way, and I couldn't get to the same throughput. If you want to see numbers, I will show them later, but I'm afraid I don't have much time right now to show you and bore you with numbers. Just trust me that the same thing on GlassFish was quite a lot more performant, almost twice as performant. So let me check how much I have time. About I think I have 10-15 minutes, so it's okay. So I want to talk about some things that I think people think about virtual threads, but they are not true or not entirely true. Some myths about virtual threads that I heard a lot of times, and I explained to people and then said, oh, this is how it works. So, okay, I didn't know. So I want to educate you a bit. One claim is that thread locals don't work because, for whatever reasons. People might think that thread locals only work on platform threads, but that's not true. They actually are a JVM concept, and JVM can emulate. For platform threads, it uses operating system concepts. For virtual threads, it basically uses plain Java, but it can isolate thread local so that when you store a thread local value in one virtual thread, it's not visible in another one. So it's completely isolated for virtual threads, and you can use them as you use them with platform threads. But there's one catch. Usually you create a lot more virtual threads, or at least that's the promise. You can create millions. I think that in reality, no one will create millions of virtual threads because then it doesn't scale so much. I did measurements, and when I created like 10,000 of them and 100,000 of them and tried to run the same thing on them, it wasn't faster. because then you have a lot more tasks you need to switch, and then there are some context switches, even if they are in a Java virtual machine. Java virtual machine still needs to do the context switches, and even although they are faster than CPU context switches, if you create a lot of threads, then it adds up. So I think in reality you would use like 10,000, 20,000 virtual threads and no more. But even in that case, if you forget to remove something from thread local, it will be there in the virtual thread until it's stopped. Again, virtual threads will be stopped probably much sooner than threads in a thread pool. But still, if you create a lot of threads and each of them creates a virtual thread local variable and stores something to it, we have like 10,000 or 100,000 copies of it. So don't overdo it. I would say don't overuse virtual threads. Don't create like millions of threads. Only if you have a specific case when you create short-living threads, you do them, they do something really fast, and then they are done. Then maybe millions of threads is fine. But if they live for a longer time, it's not very safe. And another thing is that it's not very obvious. But I discovered it in some frameworks, and also Grizzly, the HTTP stacking GlassFish uses thread locals in a way that they are used to cache some things that are expensive to create, like simple date formatter or some objects that can be recreated, but it's useful to cache them. And when they are already created by a thread for one task, another task can reuse them because it doesn't change. It was already created. It's worthless to throw it away and create it again if it's the same thing. So when you have like 100 threads in a pool, each of them has their own copy of simple date formatter, but it's better than having one shared, because simple date formatter is not thread safe. So it's good to put them in a simple date formatter in a thread local variable, then it's safe because it's accessed by just one thread. But it's not going to be recreated again, because the thread, when it's done with the task, it's in a thread pool, so it's going to be reused for another task. And if the second task needs simple date formatter or some other heavy object, it's already there. With platform threads, if you implement the approach that you create a platform, virtual threads. With virtual threads, if you work with them the way that you create a virtual thread for every task, and the framework was designed to improve performance by caching in thread locals, then you lose these performance improvements. Because then every thread, every task will create this object again and again. So with some legacy frameworks that already rely on thread pools, thread pooling mechanism, you can actually decrease performance. It will not ruin your application, but it will make your application slower if you use virtual threads and these frameworks. So just to clarify what it means when you use thread locals in virtual threads. It's not unsafe, but it can decrease performance, either improve or increase memory usage, or degrade speed of your application. But only if they are misused. If you use them for valid reasons, you can safely use them in virtual threads. Sorry. I think I made a mistake. I missed one slide. So I will just talk from my memory. So another myth is that you should avoid the word synchronize or synchronize blocks. And what some people believe is that if a library uses synchronize, it's not possible to use with virtual threads, or it degrades performance automatically. That's not true. If you have synchronized blocks in your application or in a library, maybe you don't even know that it uses synchronized. It's not automatically going to ruin your application if you use virtual threads, because synchronized is only a problem in two cases. When within a synchronized block you do an I operation, which is a blocking operation that normally would cause that the virtual thread is removed from the underlying system thread, and another thread would be scheduled. But if it's in the synchronized block, JVM cannot do that for whatever reasons. And I think there are no it's not impossible to overcome them. I think they are going to fix this in newer versions of Java. But with Java 21, there is this limitation, at least in OpenJDK. And instead of that, if you really want to make this have the top performance with virtual threads, it's recommended to use reentrant locks, which work in the same way. It's just you have to create an object and then use it to lock your block, and then the semantics of reentrant block and synchronized is the same way. It just synchronized are implemented via some native code and some other means that currently prevent removing running threads from these underlying platform threads. But this actually doesn't happen very often, because it's quite dumb to create a synchronized block and then call a database or read from file from disk, because then you synchronize for a long time already, and some other threads, if they want to access this code, they have to wait. So your application is already not very performant, because if multiple threads want to access this piece of code, they usually have to wait for a longer time than just for short synchronization time, because of the I/O operation inside. So in reality, you don't need to think about this too much. Another case when it's not safe to use synchronized with virtual thread is if within the synchronized block you do a native call to a Java or to a C library or some other language. That's again not very often. Like who did a native call in their life? I never did. I don't know if anybody did some native calls to JNDI. You probably also know that it's very rare, and it's very rare to do it in a synchronized block. So again, it's some truth to avoiding synchronized with virtual threads, but actually the danger is only in very edge cases, which most probably don't happen in your life. Then the third myth is that you can just replace platform threads with virtual threads, and you're done, and your application is better. If you listen to me carefully, I hope you're not asleep already. You probably already know that it doesn't work that way. Sometimes when you replace a platform thread with virtual threads, you can have performance degradation for the reasons I mentioned about thread locals. If some library uses it for caching, then with virtual threads, you can lose this performance improvement. But it's not going to ruin your application. If you do that, maybe your application will be less performant. Maybe if you have this rare case that synchronized block calls an I/O operation, then you will see some performance degradation, because then the platform thread will be actually blocked and no virtual thread could use it. But there are some other platform threads, and virtual threads can create some more. It can detect if some platform thread is blocked for a longer time. It can create more platform threads to compensate for it. So in reality, this is really not an issue. But still, test your application. If you switch to virtual threads, test your performance first. It shouldn't ruin your application, but it can degrade your performance. And if you want to improve performance, as I mentioned before, use reentrant locks if you can to replace synchronized blocks. And another thing is reactive programming, which I mentioned earlier. Reactive programming, maybe I will show you the code if I have an example. I wanted to show you how it actually works and what it feels like if you haven't seen that. Where do I have it? Here? No. No, don't remember where I... Okay, here's an example. It's not the one that I wanted to show you, but here's an example how it looks like. So you create basically a pipeline that handles some events that come to your application, and it's more efficient if you create a pipeline that reacts to some event, then does something, then when some other event happens, you can map. It resembles streams in Java, but it's the other way around. With stream, you build a pipeline, and at the end, you call like toList or collect, and that's when all the operations are executed. Here, you create a pipeline, and when there is an event, the pipeline is executed, but then when there is another event, it's executed again. So it's different way how you trigger the execution. With streams, you trigger all the execution at the end when you want to like go through the stream and collect it to something. With reactive pipeline, you do it by one for each thing that happens, and you can keep the reactive pipeline running all the time and listening for incoming events. But it's quite efficient because it uses only small thread pool and executes asynchronously all the tasks. And it doesn't, ideally you shouldn't block in the thread pool. That's the only major concern and limitation, that you need to use asynchronous API. You need to use different API. If you use blocking APIs and you block your thread, it's still a platform thread. You will reduce the number of threads that can process the pipeline, and they are already limited. They're, again, something like the number of CPU cores. So if you block several of them, you really decrease the throughput of your application. If you don't block them, they are efficiently used to process all the incoming tasks. But the code is like this. It's not easy to read. You have all these map, do on next, do finally, and instead of normal things like try catch or read, write, you have to do these concepts. You always have to switch from normal way of doing things to reactive way of doing things. When you have a library that accepts normal code, you have to convert it to a normal value. When you have a reactive library, you do have to do the opposite. So it's quite complicated to do efficient application with this way. And then I don't want to go into details when you need to debug something where you don't even see your line of code in the stack trace. Because there's nothing like your code is executed or your code is not in control. The pipeline is in control, and if the pipeline has a problem, you only see the framework libraries or framework classes in the stack trace, but your code is just waiting there to be executed somewhere. But virtual threads are not here entirely to kill reactive programming. At least I think there is still a lot of value in reactive programming, but not entirely in the existing frameworks, but the approach. Because with reactive programming, the aim is to create responsive application, not only application that is performant, but that is responsive, so that when somebody clicks a button, they don't have to wait all the time. They see what's happening. The application is not blocked for them. It responds. While doing something in the background, it still can do something like show progress on the screen, or inform some other service about the progress, or even handle failures. If there is some failure, it can restart the processing and things like that. So the concept is there. Again, also back pressure. That's a concept that was introduced by reactive programming, but it doesn't have to be implemented with reactive APIs. The back pressure concept is basically when your service is overloaded and is not capable of getting more and more events, it tries to notify the other services that are sending the events, please pause sending events. I'm too overwhelmed. I will respond later, but now, for some time, don't send me the events. And then the other service can pass this information to another service that is sending events to it. So it can like pause everybody. It's like when everybody tries to go to a bus that is full, they pile up in the door, but then somebody has to say, like, go back, we need to queue in the line, because otherwise we will be stuck in the door. So this is a similar thing, like this information propagates through the system, and this is very convenient, especially in systems where there are multiple services that communicate. And this is not going to happen just with virtual threads. virtual threads make your application performant, but you still need to detect when your application is just too much consuming CPU or there's too much memory consumed. You cannot process more tasks because otherwise you run out of memory or you're already 100% CPU. There needs to be some concept to notify other services to pause sending me events or because I cannot process them. And you can do that with reactive programming, but then you cannot really benefit from virtual threads. But with virtual threads, I believe there will be some new libraries or frameworks that will support virtual threads and will add back pressure and other things to make applications responsive. What you will not get is fine control over thread utilization, because virtual threads basically are trying to abstract you away from platform threads. You can't even access platform threads. I'm not sure if you can know how many threads are there created by virtual machine, but you cannot modify their amount. You can only set, when you start the Java virtual machine, you can specify like how many platform threads for virtual threads it should create. But after you start your application, you cannot do anything about it. So virtual threads were created to create an abstraction, to make our life simpler and still create performant applications, but not to get like top performance. For that, you maybe still need reactive. Maybe it's better to use, now that we have virtual threads, it's better to use or to create some reactive library that builds on top of virtual threads. I think that there are multiple options like everywhere with Java, and I think it's a good thing. So with this, if you have any questions, I'll check also in Slido. There's one question, so I'll start with that. Do we need to clean up thread locals when using virtual threads? Answer is pretty short, yes. You need to do that. Okay. Actually, no. When you create virtual threads just for some task and then you're done with the task, you don't need to do that. So I'm sorry, I went too fast into the answering. With platform threads, you need to do that if you reuse them. If you don't reuse platform thread and you throw it away after it's done with the task, you also don't need to clean it up because it's going to be cleaned up. But if you reuse a thread for some other task that is not related to what you stored in the thread local before, then you still keep what the previous task added into the thread local, and nothing is going to remove it until the thread is done. But with virtual threads, you usually create a virtual thread for a task, and then you kill it or leave it die, and then it also clears thread locals. So there, you don't need to think about thread locals or removing thread locals too much. Any other question? Okay, so if you don't have any further questions, if you still have questions later, you can find me at the conference. If you'd like to talk about Java, Jakarta E, GlassFish, come to me and we can talk after the talk. I have some t-shirts if you like them. And with that, I have one more question here. So if you don't mind, I will still answer it. Should we keep using semaphores to control virtual thread executions? Yes. Semaphores are okay. Actually, they are recommended by Java architects to use for limiting the number of virtual threads. So with platform threads, you have thread pool. Thread pool does two things. It limits the number of threads created, and it also reuses them. With virtual thread, you don't need to reuse them, but it's still good to keep their number at a certain level, because otherwise you will need a lot of memory. You may overload the system. CPU can go 100% because you will do so many things in parallel. So to make the application more efficient, it still makes sense to limit the number of threads, virtual threads. And for that, Java architects recommend using semaphores. Semaphores have only one or two downsides. One is that the amount of threads that they can synchronize is only 32 million, I think. So if you create more, you cannot synchronize them, but Probably you won't do that. And another more significant thing is when you create a semaphore, you give it a number of threads, or the maximum number of threads, but you cannot change it later. So with thread pools, you usually can change them on the fly, or some thread pools you can change them on the fly. If you want to dynamically increase the number of threads in the pool, you just reconfigure the thread pool, and then it allows to create more threads. With semaphores, you cannot do that. You would have to like somehow reconfigure do some more logic than just use semaphore. But yes, semaphores are perfect for virtual threads. Okay, so I think I'm already over time. So have a nice evening and enjoy the conference. And I'll be happy to talk to anybody of you if you come to me. Thank you.